In this episode, we take the idea of decision-making from the previous lesson and extend it into repetition, because a large part of administration is doing the same careful action across many items without losing consistency. Loops are how Bash scripts repeat work, and the Linux Plus exam expects you to recognize common loop forms and reason about how they behave, especially when inputs are imperfect. What makes loops dangerous is not the syntax, but the fact that a loop can amplify a mistake, turning one wrong action into hundreds of wrong actions in seconds. What makes loops valuable is the exact same thing, because when a loop is designed carefully, it can apply a safe, repeatable action across many systems, files, or checks without human fatigue introducing errors. The goal here is to build an administrator's mental model for while, and until loops, and to connect that model to real use cases like iterating over lists of items, waiting for a condition to become true, and retrying operations in a controlled way. By the end, you should be able to describe how each loop works, why certain loop choices are safer, and which loop style fits a given scenario. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. A good starting point is to understand that loops exist because humans are inconsistent when repeating steps, and inconsistency is a reliability and security problem. If you need to check permissions across a set of directories, verify that a service is running on multiple hosts, or apply the same configuration adjustment to many files, doing it manually invites missed items and typos. A loop provides a consistent structure. Choose a collection, perform an action on each element, handle errors, and report results. That consistency is especially important in security contexts because incomplete repetition can leave gaps, such as one host not patched or one directory left world writable. At the same time, loops demand discipline, because one incorrect expansion or one incorrect path can cause a loop to operate on the wrong set of items. This is why safe scripting habits like careful quoting, clear variable naming, and explicit validation become even more important when you introduce repetition. When you think of loops as consistency engines that can either reduce or amplify risk, you naturally approach them with the right mix of confidence and caution. A for loop is often the first loop learners encounter, and conceptually it iterates over a list of items, assigning each item in turn to a loop variable and running the loop body for each one. The list might be hard-coded, produced by a command, or derived from a set of file names, and that flexibility is part of why for loops are common in administration scripts. The key beginner understanding is that the shell must decide what counts as an item, and that decision depends on how the list is constructed and on how expansion and word splitting behave. If items can contain spaces, a naive list will be split incorrectly, and the loop will treat one intended item as multiple items, which can cause wrong operations on partial names. This is why for loops are often paired with careful input construction and careful quoting in the loop body. The exam often tests this indirectly by showing a for loop that seems correct until you notice how it handles whitespace or patterns. From an admin-style perspective, for loops are useful when you have a known set of targets and you want to apply the same check or change to each one. That might mean iterating over service names to verify they are enabled, iterating over configuration file paths to confirm permissions, or iterating over user accounts to ensure expected properties exist. The value is that the script is explicit about the set it intends to touch, which reduces surprise and limits blast radius. If a loop should operate only on a small set of known items, writing that set explicitly can be safer than trying to dynamically discover items with a broad pattern that might match too much. Beginners often chase dynamic discovery because it feels elegant, but elegance can hide risk when discovery patterns include unintended matches. A mature approach is to decide whether the loop should be strict and explicit or flexible and discovery-based, and then design accordingly. The exam-friendly answer is often the one that matches intent clearly and avoids ambiguity about what will be iterated. While loops are conceptually different because they are not primarily about iterating over a fixed list, but about repeating as long as a condition remains true. That makes while loops useful for situations where you do not know in advance how many times you need to repeat, such as reading input line by line or waiting for a service to become available. The condition is evaluated before each iteration. So if the condition is false at the start, the loop body will not run at all. This behavior is important because it shapes how you design the loop's initialization and how you ensure progress toward termination. In administrative scripts, while loops often appear in monitoring-like behavior where you check a status repeatedly until it changes, but you must always design such loops with a clear plan for avoiding infinite repetition. Beginners sometimes write while loops that can run forever when a condition never becomes true, which can waste resources or cause scripts to hang in automation pipelines. A safer pattern includes time limits or maximum retries, but the core concept is simply that while loops are condition-driven repetition, line-by-line processing is a classic use case for while loops because scripts often need to handle inputs that are naturally structured as lines, such as lists of hosts, lists of paths, or extracted report outputs. The key idea is that while can repeat for each line read, allowing the loop body to treat each line as one unit of work. This can be safer than a for loop over a command output when the output contains spaces, because line-oriented reading can preserve each line as a whole item. Even without writing code here, you can appreciate the intent. Preserve the structure of the input so the loop processes the same units a human would see. This is another example of how loop choice intersects with expansion and splitting rules. If you expect each item to be on its own line, a line-oriented loop aligns better with that reality than a whitespace splitting list. The exam might not require you to write the syntax, but it often expects you to know which loop style is appropriate for which kind of input. Until loops are like the mirror image of while loops, because they repeat until a condition becomes true, meaning they continue while the condition is false. This is useful when you are waiting for something to happen and your loop's main purpose is retrying until success. For example, you might repeatedly check whether a network service is reachable or whether a file has appeared, and you want to stop once the desired condition is finally satisfied. The until form can read more naturally in those cases, because the loop's name matches the intent. Keep trying until the goal is reached. Beginners sometimes ignore until and use while with inverted conditions, which works but can be less readable, especially when conditions are complex. Readability matters because loops are already mentally heavy, and a double negative condition inside a while can be difficult to reason about under stress. For exam purposes, you should recognize until as a loop form that expresses a retry until success pattern, and you should be able to explain that it is evaluated before each iteration like while. Loops and conditionals often work together, and that combination is where scripts become powerful, but also where they can become risky if boundaries are unclear. In real admin-style logic, you might loop over items, and within the loop use if statements to handle different outcomes, such as skipping items that do not meet prerequisites, reporting warnings, or taking different actions based on observed state. This pattern supports robust behavior because it allows the script to continue processing other items even if one item fails, while still recording the failure. The risk is that error handling can become inconsistent if each branch treats failures differently without a clear plan. A good structural habit is to decide what a failure means for the loop as a whole, such as whether one failure should stop everything or whether the loop should continue and summarize errors at the end. That decision depends on the task and the risk, and the exam often tests that kind of judgment by describing whether partial success is acceptable. When you design loops with intentional error handling, you avoid brittle scripts that either stop too early or continue too dangerously. A major loop safety topic is termination, because the most common loop bug is a loop that never ends or ends too late after causing unintended damage. For fixed lists, termination is simple because the loop ends when the list is exhausted, but you still must ensure the list is correct and not unexpectedly huge. For condition-driven loops like while and until, termination depends on the condition changing over time, and if it never changes, the loop can hang indefinitely. In administrative use cases, waiting loops should have a maximum wait time or retry count, not because you distrust the system, but because you want predictable behavior in automation pipelines and in troubleshooting contexts. Even in manual use, an infinite loop can create confusion because it may look like the script is doing something when it is actually stuck repeating the same failed check. Designing for termination is part of treating scripts as reliable programs rather than as casual text. The exam-friendly mindset is that safe loops include clear stop conditions and do not assume the environment will always behave as expected. Another safety dimension is output and logging during loops, because loops can generate a lot of messages quickly, and too much output can hide the important signals. A well-designed loop provides enough feedback to show progress and highlight failures, but it avoids spamming redundant lines that make it difficult to spot actual problems. This is especially relevant in pipelines, where logs may be your primary evidence of what happened after the fact. In a loop that processes many items, it can be helpful to include context with each message, such as which item is being processed, so you can correlate errors with targets. At the same time, you should avoid leaking sensitive data in loop output, because loops often touch files, accounts, and network paths that can reveal environment details. This connects back to the broader security mindset of minimizing unnecessary exposure while still maintaining accountability. The exam may not test logging format, but it will test the idea that scripts should be readable and that behavior should be traceable, and loop output is part of that trace. Performance and resource usage also matter because loops can make scripts slow or heavy if they repeatedly run expensive commands unnecessarily. A common beginner pattern is to recompute the same data inside a loop on every iteration, which can cause a script to take far longer than needed and create unnecessary load. A more mature approach is to gather needed information once outside the loop, store it in variables or files, and then iterate over the results. This improves efficiency and also improves predictability, because fewer repeated external calls means fewer opportunities for transient failures to derail the script. Another performance consideration is how many iterations you are actually performing, because a loop over a broad pattern might include far more items than you intended, which can turn a simple maintenance task into a long-running job. That is another reason to prefer explicit lists when scope should be narrow, and to validate discovered lists when scope could be broad. The Linux Plus exam often rewards this kind of thinking when it asks about safe automation practices rather than specific syntax. Loops also interact strongly with quoting and variable handling, because loop variables often hold paths or user-derived values, and those values must be handled safely. If you expand a loop variable unquoted, whitespace can split it into multiple words, and wildcard characters can expand into unexpected file lists, which can lead to operations on unintended targets. This is how a loop can magnify a small quoting mistake into a large destructive mistake. A safe scripting mindset treats loop variables as untrusted input, even when they come from file lists, because file names can contain odd characters, and because command output can contain unexpected whitespace. This is one of the most practical reasons the earlier expansion and substitution topic matters, because loops are where those rules have the biggest impact. For Linux Plus reasoning, you should be able to explain that safe loops protect variable expansions and validate scope, because the loop's power demands careful boundaries. When you see an exam question about a loop that handles file names, the correct answer often involves preserving each file name as a single unit rather than letting the shell split it unpredictably. Waiting and retry loops are another important admin-style pattern because many services take time to start and many dependencies become available asynchronously. A script might need to wait for a port to become reachable, for a file to appear, or for a service to report healthy status, and loops provide a structured way to implement that patience. The safe way to do it is to avoid aggressive tight loops that consume resources and to include a clear limit so the script eventually stops and reports failure instead of hanging forever. The key beginner lesson is that waiting is part of real system behavior, so scripts should handle it gracefully, but gracefully does not mean endlessly. This is also where until loops can read naturally, because the script is conceptually saying, keep checking until the condition you want is true. When you connect loops to practical waiting scenarios, the topic becomes less academic and more obviously useful. The exam often includes scenarios where a script must retry a check, and understanding the loop forms helps you choose the approach that matches intent and avoids unbounded waiting. By the end of this episode, you should see for, while, and until loops as three distinct ways to express repetition with clear intent, each suited to different administrative tasks. For loops, iterate over a set of items. making them ideal for applying consistent actions across known lists of services, files, or targets, provided the list is constructed safely and handled with careful quoting. While loops repeat as long as a condition remains true, making them ideal for line-by-line processing and for repeating checks when you do not know iteration counts ahead of time, provided termination is designed intentionally. Until loops repeat until a condition becomes true, making them a natural fit for retry until success patterns and for waiting scenarios, provided you still include sensible limits to avoid infinite hangs. Across all loop types, safety and readability matter because loops can amplify mistakes, so robust loops validate scope, handle errors consistently, and provide traceable output without overwhelming noise. When you can explain loop choice and loop safety in this way, you will be able to interpret Linux Plus scripting questions with confidence and design scripts that behave predictably in the messy realities of real systems.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.